Today we are looking at the conditions under which a car moving in a circle will go out of control. I am joined today by Candace. She likes to go by Candy. She's new to the channel. Please welcome Candy to our channel. Thank you very much. This is a problem that we are going to look at today. Two students, Sam and Ria, wanted to drive in a circle as fast as possible without losing control of their vehicles. First of all, don't try this at home. Something like this should be left to the professionals. And if you do try it, this channel takes no responsibility for any property damage, bodily injury, or even death that may result. Sam and Ria are real people. I know them. And they wanted to do this experiment. But I told them, no way, not on my channel. As you know, this channel is a safe space for students. Let's continue with the problem. Ria was driving a 1,200 kilogram car on a horizontal road as she rounded a curve with a 40-meter radius of curvature. The coefficient of static friction between the tires and the road was 0.7, and the coefficient of kinetic friction was 0.4. Part A. At what speed will Ria lose control of the car? Part B. Sam thought she could safely make the turn at the speed calculated in Part A because she drives a much more massive truck. Is her reasoning correct? Explain why it is or is not correct. That's the problem. Now, Candy and I will go and solve the problem. See you soon. Candy and I are back, ready to solve the problem. The first step is to draw a picture of the situation. This is the circular loop that the car will go in, looking down from the top. This yellow rectangle represents the car. And here's a coordinate system that we will use. The horizontal axis is the x-axis, and the vertical axis is the z-axis. And the y-axis is coming out of the page. The car has a velocity v, which is tangent to the circle. And as the car goes around in a clockwise direction, the direction of the velocity is going to change. It's always going to be tangent to the circle. And the magnitude of the velocity will be the same because it's moving at constant speed. Since it is moving in a circle, there is an acceleration directed towards the center of the circle as shown here. This is the centripetal acceleration. Since it is going at constant speed, there is no acceleration tangent to the circle. There's only centripetal acceleration towards the center of the circle. To find out more about acceleration in circular motion, please see the video, Acceleration in Circular Motion, starring Giselle the Gazelle. Now let's draw a side view diagram, and what we want to do here is to draw a free body diagram showing all the forces acting on the car. Now here, the x-axis is the horizontal axis, and the y-axis is the vertical axis, and the z-axis is out of the page. This dot represents the car, and I will draw all the forces acting on the car. First of all, we have the direction of the acceleration. It is in the positive x direction, directed towards the center of the circle. The force of gravity acts downwards, as shown here, and then we have the normal force acting upwards. That is a force which the road exerts on the car. Now, since the acceleration is directed in the positive x direction, there must be a force in the positive x direction. And that force is a force of static friction, as shown here. Yes, Candy? That's a good question. Candy's wondering why we use static friction instead of kinetic friction, because the car is moving. Shouldn't we use kinetic friction since it's moving? That seems to make a lot of sense, but actually it is static friction. Let's look at that question in more detail. Let's consider a wheel which is skidding on the road, like this. Note that the wheel is not turning, it's not rotating, it's just moving in the horizontal direction. This is what would happen if Rhea were to suddenly slam on the brakes. The wheel stopped turning, but the car keeps moving to the right. And one thing you'll notice for this is that there is relative motion between the wheel and the road. The wheel is sliding across the road. And when two surfaces slide across each other, we must use kinetic friction. Here's another example where we use kinetic friction. Here's a wheel that is rotating in place. It's just rotating, not translating. You may have experienced this if you ever got your car stuck in the mud. The wheels turn, but you don't go anywhere. This can also happen if you're stuck on the ice. Wheels turning, but no forward motion. If you look closely here, you can see that there is relative motion between the road and the point of the wheel that touches the road right here. The two surfaces are sliding across each other. So again, this is a case of kinetic friction. But here's where we have static friction. The wheel is rolling on the road, like this. Look closely here. There's no relative motion between the road and the point of the wheel that touches the road. Look carefully. The wheel does not slide across the road. So this is a case of static friction. There's no relative motion between the two surfaces in contact. Yes, Candy. Oh, Candy wants to look at that in more detail. She's still not sure why we use static friction in this case. Okay, Candy, I wasn't planning to go into such detail in this presentation, but you have the question, so I'm here to answer your questions. Let's look at that in more detail. When the wheel rotates on the surface and it rolls, and there's no relative motion between the wheel, the point of the wheel in contact with the road, we say that the wheel is rolling without slipping. Here I want to find the conditions under which the wheel rolls without slipping, and that's the condition under which we can use static friction for the force of friction. So in a time delta t, the wheel rotates through an angle delta theta, as shown here. Here's our delta theta. And there is an angular speed associated with this rotational motion. And the angular speed omega is delta theta over delta t. It's the rate of change of the angle theta. And this is the radius of the wheel, r, and this, s, is the arc length subtended by the angle delta theta. And the relationship between these three variables is s equals r delta theta, where delta theta is in radians. That's the definition of a radian. Now this wheel is moving to the right with a velocity v as well as rotating. This is a condition for rolling without slipping. In the time delta t, the center of the wheel moves a distance delta x equal to the arc length. If this condition is true, then the wheel is rolling without slipping. Let's apply that condition. The velocity is delta x over delta t. But if it's rolling without slipping, delta x is equal to s, the arc length. So we can write the velocity as s over delta t. But look at this. S is r delta theta. So therefore, the velocity is r delta theta over delta t. But look at this. Delta theta over delta t is the angular speed. So we get that v equals r omega.
This is a relationship between translational velocity and angular velocity if the wheel rolls without slipping. Yes, Candy. Candy wants to go into even more detail for this situation. She's still not clear how we can say that the velocity of the wheel at the bottom part here is 0. She's not convinced. Okay, Candy, as I said before, I don't have a lot of extra time in this presentation to go through this, but you asked a question, so I'm going to go through it for you, okay? Let's consider the velocity with respect to the road. Every point on the wheel has a velocity with respect to a reference frame in the road. That's the velocity with respect to the road. Now, as the wheel rolls without slipping, the center of the wheel moves at velocity VCR equals V with respect to the road. So right here, VCR means velocity of the center of the wheel with respect to the road. And as shown here, it is directed towards the right, and its magnitude, it is equal to V. It has a magnitude of V. Now, all points on the rim of the wheel, all these points on the rim, they have a velocity VPC of magnitude V with respect to the center of the wheel. So VPC means velocity of the point on the wheel with respect to the center of the wheel. And I show them right here. They all have magnitude V, and they are all tangent to the rim of the wheel, as shown here. Now, we want the velocity of a point on the rim of the wheel with respect to the road, and that's given by this vector sum. VPR equals VPC plus VCR. So let's see what this means. Velocity of the point on the wheel with respect to the road equals velocity of a point on the wheel with respect to the center of the wheel plus velocity of the center of the wheel with respect to the road. This relationship is just the Galilean transformation of velocities between two reference frames. What we are particularly interested in is the velocity, VPR, velocity of the point on the wheel at the bottom of the wheel with respect to the road. We want to see that that velocity is equal to 0. And then we can say that that bottom part of the wheel is at rest with respect to the road, and we can use static friction. So let's look at the point at the top of the wheel, and let's apply that formula. VPR equals VPC plus VCR. At the top of the wheel here, VPC is equal to V. It's directed towards the right. So let's put this relationship in our expression. So VPR is V, velocity of the point on the wheel with respect to the center of the wheel, plus VCR, which is also V, velocity of the center of the wheel with respect to the road. So we get 2V. So the point at the top of the wheel has a velocity of 2V with respect to the road. Now let's look at the point here at the bottom of the wheel. For the bottom of the wheel, VPC equals negative V. It's going in the other direction, towards the left. So let's substitute that into this expression. So we get negative V plus V, which is 0. So the velocity of the point at the bottom of the wheel with respect to the road is 0. Let's look at what we found for these 3 points on the wheel, the top, the center, and the bottom. As the wheel rolls without slipping, the top of the wheel moves at velocity 2v with respect to the road. VPR equals 2v. The center of the wheel moves at velocity v with respect to the road. VPR equals v at the center. And the bottom of the wheel is at rest with respect to the road. VPR equals 0. So it is at rest with respect to the road. I think something exciting is about to happen. That was exciting because now we're going to find out what is the friction for a rolling wheel. Since the bottom of the wheel is at rest with respect to the road, when the wheel rolls without slipping, right here, VPR equals 0, the friction between the wheel and road is static friction. Candy, do you have any more questions? That's good. You asked a lot of questions today, and as you know, I wanted to get through this thing a little bit more quickly and get on to the problem. I would appreciate that in future you don't ask me so many stupid questions. I want to get on with the presentation. Do you understand? I'm sorry about what just happened. As you can see, Candy is gone. I don't blame her. I crashed out, and it's something I'm not proud of. And I do have anger problems, which I try my best to overcome. I did apologize to Candy, but she still had to leave, and that's fine. I don't blame her. I probably would have left as well. For those of you who are still watching the video, I would like to apologize for what just happened. Obviously, a teacher should not yell at students or tell them that they have stupid questions. A teacher is supposed to welcome questions from students. And so I apologize for that. I have left that in the video. I could have easily edited that out of the video, but I've left it in because I want to be honest with my audience. I need to hold myself accountable for what I've done. And maybe you'll stop viewing this video. I probably lost half my viewers already, maybe even more. And maybe you're going to cancel your subscription. But I need to be honest. And I would just like now to apologize to the viewers of this video for what just happened. It was wrong, and I'm going to try not to let that happen again. Okay, so let's continue solving this problem. I'm going to solve it on my own without Candy now. This is our free body diagram. We have the three forces. And these are the things which we know. We know the mass of the car, 1,200 kilograms. The radius of the circle is 40 meters. Coefficient of static friction was 0.7. Coefficient of kinetic friction was 0.4. And what we want to find is the maximum speed before the car goes out of control. I put this in a problem because I wanted the students to be safe. You know, I think maybe my channel is not such a safe space, because when teachers yell at students and when teachers tell students not to ask so many stupid questions, that's not a safe space, is it? So I should have just told Rhea and Sam to go out there and go crazy and drive the car in a circle at maximum speed, because that's unsafe, but the video is also unsafe. It's not a safe space. I apologize for that. I'm going to make a pledge to this audience that I will make my channel a safe space going forward. I will do my best to make it a safe space. I'm sorry about what happened. Okay. Rhea and Sam, if you're listening, don't really drive the car, okay? Be safe. Just solve the problem. Thank you. Okay, let's keep going. So the acceleration is directed towards the center of the circle, towards a positive x direction as shown here. Now, we need to apply Newton's second law. That's how we solve these problems. So Newton's second law, the sum of forces in the x direction equals mass times the acceleration in the x direction. So I'm applying Newton's second law in the x direction. And later on I'll apply it in the y direction. So The force in the x direction, there's just one force. It's the force of friction static. So right here, Fx equals force of friction static. Now when something is going in a circle, the acceleration is centripetal acceleration, which is equal to v squared over r. So Ax is v squared over r. So Newton's second law becomes this. Ffs equals mv squared over r. Now, I need to find the force of friction. Force of friction, static, varies from 0 up to μs times the normal force. Look at this. If you increase the velocity, what do you have to do? You need to increase the force of friction. So the maximum velocity will have the maximum force of static friction, which is here, μs Fn. So here's what I shall write. Maximum force of friction static equals m Vmax squared over r. Now let's put in what the maximum force of static friction is. It's μs Fn. So we get μs Fn equals m Vmax squared over r. Oh, look who's here. Come over here. She's back. Candy, I am so sorry for what happened. I'm going to work better from now on to control my anger issues. I'm really sorry about what happened. I'm so glad you're back. I really want you in this presentation. Thank you so much. Okay, so now go down there and let's continue this presentation, okay? Thanks. I'm so glad she's back. There she is. Thank you so much. Welcome back, Candy. Thank you very much. So this is what we have, and now we need to find what the normal force. So let's find the normal force. So here's our equation. Now to find the normal force, we should apply Newton's second law in the y direction. Sum of forces y equals m-ay. Sum of forces y. Let's take the upwards direction to be positive and the downward direction to be negative. So this summation is going to be Fn minus Fg. Negative in front of Fg because it is pointing downwards. And the acceleration in the y direction is just 0. So Fn minus Fg equals 0. Solve for Fn. Fn equals Fg. And Fg is just m times g. So let's put this mg into here for Fn. And this is what we get. Mu s mg equals m v squared max over r. Notice here that we have m on both sides of the equation. So let's cancel these m's on both sides of the equation. The result doesn't depend on the mass. So we make that cancellation and then we solve for Vmax. And we get this. Vmax equals square root mu s times rg. Now we've got our equation. We need to put in our numbers and find what the actual maximum velocity is. There's our expression. Let's put in the numbers. Mu s is 0.7. R is 40 meters. G is 9.8 meters per second squared. And we get 16.6 meters per second. So now we can answer question A. If Rhea drives at a speed greater than 6.6 meters per second, then she will lose control of the car. Because at a speed greater than 16.6 meters per second, there is not enough static friction to provide that force towards the center of the circle. So the car will go out of control. Now let's look at the effect of mass. In the derivation of the maximum velocity, we found mu s mg equals m v squared max over r. Mass canceled out, so that the maximum speed did not depend on mass. And we found that Vmax was square root mu s rg, independent of mass. So now we can answer question B. Sam will still go out of control at the same speed as Rhea, even though Sam drives a much more massive truck, because the maximum speed does not depend on mass. Thank you very much for listening to this presentation, and I don't blame those viewers who had to drop out after what happened in this presentation with the crash out and everything. I really apologize for that. But I didn't enjoy making this video. I don't think Candy also didn't enjoy making it. It was not enjoyable, but I hope you learned something from it. And I'll try to be better next time. So thank you very much. I'm not going to ask you to subscribe after what happened. If you do subscribe, that's great, but I understand if you don't want to subscribe. And if you need to cancel your subscription, I do understand. So thanks again. See you next time. Bye.